Okay, so story aside, we have here a some path, and there's a starting point and an ending point. And let's see here, in any given little bit of this curve, inside of that little bit of curve, the amount of, we have given to us heat absorbed per unit distance. And so therefore the total amount of heat absorbed, which I'm going to call, well, the total amount of heat absorbed in that little piece, I'm going to call that dE. I can't use H because H is this given function. The amount of energy, let's say, that's absorbed in there is this, heat per unit distance times distance. Does that make sense? Okay. So if you want to know the total over the entire curve, the total amount of heat absorbed, well, we just add up over the entire curve the amounts of heat that are absorbed on each little piece, which, as per above, is this H function ds. Now, for number 4 here, we're actually going to compute this. So we've got to parameterize this curve. And parameterizing the curve, I can then plug in and evaluate this thing. So let's do that. Well, conveniently, this is a given as a graph of a function. So I can use the graph parameterization, and I can say, let's see here. Let's see here. So y seems to be a function of x, but no discussion of z. I guess z is 0. So our parameterization is, we're going to have x equal t, y equals, well, it's f of t, so it's going to be, let's see, 1 minus t squared over 4. And z is just going to be 0. Okay, everybody good? So that parameterization being done, then, let's see, what's the range of values of t? Well, okay, x goes from -10 to 10, and therefore t goes from -10 to 10. So we're going to have an integral as t goes from -10 to 10, and h depends on x, y, and z. That's x. That's y. That's z. ds, what's ds? Well, ds is the length of your derivative vector for your parameterization. So you're going to have to take this parameterization, take the derivative, compute the length of that derivative, etc. That's going to be this here, and then dt. So this is sorry, I don't know what, okay, I wrote -10 to t. I meant -10 to 10. My apologies. I don't know what I was thinking about something else there, apparently. So this is now a single variable integral. This is a single variable integral that represents this scalar line integral that answers our problem. So you just evaluate this.
I think the thing is, it's like very, very long, and it gets to a point where it's a little bit hard to integrate.
The integral's hard? Okay, let me take a shot at it. Let me see what we end up with. So, so our x prime vector, by the way, is going to be what? Let's see, it's 1. It's negative t over 2 is 0. Does it reduce?
Somewhat.
Okay. All right. I hope and expect that you're right. Let's see. So the length of x prime is, let's see, so square root of 1 plus t squared over 4. Okay. All righty. Let's see here. Yeah, I could kind of see that. Oh, yeah, I totally see that working out. Yeah, this is, okay. All right, cool. Let's do it. What's our h function? Well, okay, in the statement of the problem, h is 1 over x squared plus y squared. So we have 1 over t squared plus, now y squared is this. So when I square that out, let's just multiply that out. This squared is 1 plus, minus 2 times this, so that's t squared over 2, and then plus, t to the 4th over 16, and then square root of 1 plus t squared over 4 dt. Is this everybody cool with this? So this was that thing squared. That's our y squared. Here's our x squared. Now a cool little bit of algebra happens, and we've seen this in a previous problem once before. I think we did. So this is a perfect square, right? That's y squared. That's this thing squared. And notice that when you add t squared to this expression, all that happens is this minus becomes a plus. Is that cool? Yeah, when t squared plus negative t squared over 2 is just positive t squared over 2. So, in fact, I claim again that is a perfect square. It's just a perfect square of this with a plus instead of a minus. So let me rewrite that. Why do I keep doing negative 10 to t? I'm not sure what's going on there in my mind. That's negative 10 to 10. My apologies. Negative 10 to 10 there. Sorry. Negative 10 to 10. Okay, all right. So this denominator altogether is 1 plus t squared over 4 quantity squared. And then over here we still have square root of 1 plus t squared over 4 dt. So altogether then, notice there's a 1 plus t squared over 4 in a couple of different places. Here it's being raised to the power of, well, ultimately negative 2 because it's in the denominator. This is positive a half. So altogether I have 1 plus t squared over 4 quantity to the negative 3 halves dt. Oh, yeah, there we go. Is everybody on board?
Is that negative 3 halves? Is it?
Negative 3 halves, because this was that thing to the power of negative 2, and then here's the exponent is positive a half, so that adds up to negative 3 halves. And this is a trig substitution. This is so what you have to do is you look at what's on the inside here and you ask yourself, does that look familiar? Does that look like any trig identities that I know? And yeah, it looks like the 1 plus tangent squared equals secant squared. So I'm gonna rewrite 1 plus, this is a little sidebar over here, 1 plus t over 2 squared. I would like that to be 1 plus tan theta squared so that I can rewrite it as simply secant squared and use trigonometry identities, which is awesome. So I'm going to let t over 2 be tan theta. In other words, t is going to equal to 2 tan theta. At which point dt becomes 2 secant theta d theta. Right? And now this expression I can simplify as, well, let's see, what do we got here? We got 1 plus t squared over 4. Well, the whole point of this trig substitution was so that this 1 plus t squared over 4 would simplify as secant squared. So this thing here is secant squared that I'm raising to the negative 3 halves. So I have, let's write that down, I have secant squared theta to the negative 3 halves. That's going to simplify nicely. Then I have dt, here it is, dt is 2 secant theta d theta. And let's see here, well, altogether, secant squared to the negative 3 halves is secant to the negative 3. And here I have secant to the 1. So altogether that's secant to the negative 2. And we'll see secant is 1 over cosine, so secant to a negative power is cosine to a positive power. You get just cosine squared theta d theta, which of course is the same as, well, anyway, hopefully at this point, I'm going to leave the rest of this for you guys because this is something that I hope you guys will know how to do. Okay, is that cool? Does that make sense?
Yeah.
Everybody good? Okay. All right, so half angle formulas here. Don't forget you have your trig substitution to plug. You got to rewrite everything in terms of t and then plug in. Okay. All right. Alrighty, let's see, where's my thing?